sure you charge your mobile almost every day, or sometimes maybe several times per day. If you use a normal charger, it will take you a couple of hours. But if you use a quick charger, it takes you a few minutes. What is the difference? The quick charger has inside high-power transistors that allow to handle more current and more voltage into your device. Now imagine you have an electrical car and you want to charge it. You don't want to spend a lot of hours waiting for the charge, so you really need high-power transistors to put all this power very quickly into the batteries of your mobile. The objective of the project YESvGaN is to develop these high-power transistors that can handle 100 ampere and 1200 volt, and they are based on gallium nitride, a wide band gap semiconductor that allows to handle all this power without breaking. To characterize these materials, we use atomic force microscopy. We put the sample on the system, and with the atomic force microscopy we can also measure the surface potential with a technique that is called Kelvin Probe Force Microscopy. And we have the peculiarity that we can illuminate the sample with above band gap illumination. This is ultraviolet light for gallium nitride, and change the electrical properties of the sample with this illumination. So the laser would come through this path, go to the mirrors, and then illuminate the sample there.
Here we prepare our samples and our substrates. Since we are studying materials at the nanoscale, it's very important that they are clean for making a good measurement. And we do it through both using chemical reagents, and physical processes, using things like this ozone cleaner.
We have mounted this toy AFM here for didactic purposes in our courses, so I can tell you the different parts in which the AFM consists. We have the sample here, and we need a cantilever that ends in a tip. We also need a laser that comes here, reflects close to the tip, and goes to the screen here. In a normal setup, this screen would be made of a photodiode or 4 photodiodes that tell you how much light and how it moves when it goes to the screen. And we also need to make the cantilever vibrate. For this we have this generator here, and we look for the resonance of the cantilever. And if you have a look at this amplitude of the resonance that we monitor with the laser, when I move the sample in below the tip sample interaction increases, and this decreases the amplitude of the laser. In a normal setup with a feedback, the feedback would lower the position of the sample so that it would recover the large amplitude we had at the beginning. And this is our real system, our real AFM. We put the sample here, and we also need a laser that comes through this fiber. It is a red laser. We put the tip here. We cannot see the tip there, or the cantilever, but I have it here in this cantilever holder so that you can see it better. This is the holder, and at the end we have the cantilever. You would not see it because it is very small, but the tiny, very tiny tip at the end, it ends in only 20 nanometers. It is silicon coated with platinum. And these 20 nanometers, you would not even be able to see it in the optical microscope. And this would go, this is the head of the AFM, and it would go on top of the sample. So with the AFM, we measure the surface potential in the material. And we also measure the changes induced by light. To understand what happens with the light, we have plotted here the energy, and here is the surface of the material, and in this direction you go towards the bulk. This is the band bending, because in the surface the bands bend upwards if you have an N-type material. When you illuminate, you are creating electron-hole pairs, and through this electric field you have here, electrons drift towards the bulk, and as a consequence the band bending decreases. And what we measure as surface photovoltage is the difference between the band bending in dark and the band bending with the light on.
Hello, I am a PhD student here in the POEMAS group, and currently I am studying the analysis data from what we have measured here. And this is the topography of at nanoscale of our sample, and this is the electrical response. Summing up, what we have done is we have pinned in one of these flakes. You can see the difference between the colors. It's what characterizes the topography. And in the flake that we have pinned and have applied voltage, what we have is that it's currently active, while the other flakes are actually not.
We have a FEM in the glove box. We can measure the samples in a controlled environment for a low humidity.
In YESvGaN, we have been involved in Raman scattering measurements. Raman scattering is a technique which is sensitive to strain fields, defects, impurities, and also to the temperature of the material. So we have been studying the evolution of temperature in gallium nitride and nitride multilayers, as well as devices, as part of our work within the project.